There is one thing that is common to all the machining operations. It is chip formation. Chips are formed as a cutting tool is forced through the work material. But what is the mechanism by means of which the chips are formed? Is it shear? If so, in what direction and to what amount? And what is the extent of plastic deformation? By observing the machining of a metallurgically prepared specimen through a microscope, one can see what happens as a chip is formed. However, an interpretation of what is seen is first necessary before polished and etched specimens are viewed. This sketch illustrates a cross-section of a microscope barrel and a polished specimen. When the polished surface is perpendicular to the microscope axis, all of the light from the source is reflected up through the microscope tube. The surface then appears bright or white. The boundaries between the surface layer of grains cannot be seen on the polished specimen. However, when the polished specimen is etched with a chemical solution that dissolves this particular metal, the grain boundaries are brought out. They are seen as a network of dark lines surrounding the white grains when viewed through a microscope. These dark lines appear because the grain boundary metal dissolves more rapidly in the solution. This is due to a greater amount of energy present in this part of the metal. Thus, the grain boundary becomes a depression or valley around the grain. Light beams such as B are then reflected off at an angle and not up through the microscope tube. Therefore, the grain boundaries appear as black lines surrounding the white grains. If the specimen is over-etched, the surface of the central portions of the grains become rough, and the entire grain appears gray rather than white. If a grain is not a single phase, but rather a mixture of two or more compositions, it will also appear gray. This illustration shows a photomicrograph taken of a very low carbon steel. The grains of the material, known as ferrite, are surrounded by the network of black lines, which are the grain boundaries. The large black diamond-shaped image is a Knoop micro-hardness indentation. The small elongated gray areas are impurity inclusions. AISI 1020 annealed steel consists of two types of grains. The white grains are ferrite, as in the previous steel. The dark grains are known as pearlite. They appear dark because they consist of a mixture of two different compositions. The ferrite grains are relatively soft and ductile, while the pearlite grains are considerably harder and less ductile. The diamond-shaped image is, again, a Knoop micro-hardness indentation. In order to obtain pictures of microstructures such as these, the previously polished and etched specimens must be stored in a desiccator to prevent rusting. Before the actual chip formation is observed, the manner in which the pictures were taken should be explained. The operator removes a prepared workpiece from the desiccator. The surface to be viewed at a high magnification is indicated. The workpiece is clamped in a vise on the overarm of a milling machine. The cutting tool is clamped in a special fixture on the table of the machine. Just to the left of the tool is a metallurgical microscope, which is clamped to the same fixture as the tool holder. Thus, the microscope focuses on the tool point during the entire cutting operation. The operator attaches a still camera to the end of the microscope barrel. A motion picture camera was also attached in a similar fashion. To prevent vibrations of the machine motor from blurring the image, a special gear train was arranged. One of the important variables in the chip forming process is the rake angle. It plays a vital role in efficient chip formation. This sketch illustrates the commonly used nomenclature for describing chip formation during machining. There are 4 specific details the viewer should look for when observing the actual chip formation process. They are slip lines, a dark band, horizontal cracks in the direction of cutting, and incremental shear along an inclined plane. When cutting commences in 1020 steel, Slip lines form in some ferrite grains several grain diameters ahead of the tool. Slip lines form on the surface of a polished grain during the first stages of plastic deformation. As the cutting proceeds, slip lines continue to form a considerable distance ahead of the tool. The dark band beneath and in front of the newly machined surface is the second detail to look for. The portion which curves upward toward the original surface moves a considerable distance in front of the tool during cutting. The presence of the dark band is easy to explain. When the light from a metallurgical microscope, such as A in the sketch, strikes a smooth perpendicular surface, it is reflected up through the eyepiece and the surface appears white to the eye. However, a beam of light such as B that strikes an inclined surface is reflected outside the microscope, and that surface appears black and is unseen. If only the microscope light is used, the plastic deformation region and the chip would simply show up as a black, featureless area. However, when supplementary diffuse light of the proper intensity, represented as C, is used, the features of the plastically deformed metal are visible. Due to the absence of the microscope light on these areas, they appear darker. The third detail to look for is cracks in the workpiece extending from the tool point in the direction of cutting. Sometimes these cracks are very long, and at other times they are short or non-existent. But even with the absence of a crack, it can be seen that the metal where the crack should be moves in the cutting direction with respect to the metal just beneath. The fourth and last feature to observe is incremental shear along an inclined plane. The shear crack eventually angles up from the tip of the tool to the original surfaces some distance in front of the tool. Note that this shear does not occur simultaneously along the entire length of its path. This shear path is referred to as the shear plane. To see the actual chip formation, watch a 1020 steel as it is being machined. The tool, located at the upper left corner, extends a distance of 12/1000ths of an inch below the work surface. Cutting begins as the tool moves toward the work specimen. Note the formation of slip lines in the large ferrite grain in front of the tool as deformation begins. In order to clearly see the slip lines that first form during machining, the action must be stopped to study a few specific grains. At the time of the tool's first contact with the specimen, the grains encircled do not contain any slip lines. As the tool progresses a very short distance, actually less than 1 grain diameter into the workpiece, slip lines originate on the surface of the encircled grains, which are a considerable distance in front of the tool. As the tool advances, slip lines appear in more and more grains. As cutting continues, the dark band that indicates massive plastic deformation becomes more apparent. Note also the formation of slip lines beyond the dark band. To observe the bulk metal flow at the tool point, cutting at a lower magnification is necessary. This is a finer grained 1020 steel cut at a slower speed. Notice how the metal flows at the tool point. Imagine a horizontal line extending to the right from the bottom of the tool point. Notice how the metal immediately above this line and close to the tool face moves to the right and upwards with respect to the material just beneath this imaginary line. This indicates shearing in the direction of cutting in the immediate vicinity of the tool point. The horizontal shearing occurs during much of the cutting time. The shearing is so severe that the metal actually separates or fails along this line. Such a separation should appear as a crack if the two separated faces are far enough apart. Many such cracks can be seen at the tool point in this sequence. The cutting is again interrupted to look at a still photograph of such a crack. The crack is outlined in white. It is about 20/1000ths of an inch long, and the depth at which it was formed is about 12/1000ths of an inch. While cutting continues, one can observe the continued formation of horizontal cracks, and also how some of them eventually angle upwards from the direction of cutting. When the shear plane angles up to the surface, shear does not occur simultaneously along the entire length of the inclined plane. Instead, separation of the metal occurs first at the tool point, and then the crack propagates up the inclined plane to the surface. After the crack progresses about 1/2 of the length of the inclined plane, the tip of the tool again commences to cut. During most machining operations, the metal being cut sometimes seizes or welds onto the tool point. This material has the appearance of a buildup on the cutting edge, and consequently is referred to as a built-up edge. Sometimes the built-up edge actually extends beyond the tool cutting edge, with the result that the machine surface is rough. The material now being machined is soft, commercially pure aluminum. The specimen has been over-etched to show the grain structure more clearly. Consequently, the black grain boundaries are not seen, but instead the individual grains appear as different shades of light and dark. As the tool moves through the workpiece, the plastic deformation in front of the tool and the flow of the chip up the tool face can be seen. Notice also the horizontal movement of the work material directly in front of the tool, as was present with the previous steel specimen observed. Built-up edges frequently form, and at these times the point of the tool is not in contact with the finished work surface. Rather, the built-up edge itself generates the new surface. Each built-up edge remains on the tool point for only a short period of time before it is rubbed off. The material now being machined is an aluminum alloy. The individual grains cannot be seen, but the region of plastic deformation is clearly shown by the dark band. It is horizontal near the tip of the tool, but moves forward in the form of an arc a considerable distance in front of the tool. Periodically, shear occurs, commencing at the tool point, moving horizontally for a short distance, and then angling up to the surface. Now, a commercially pure molybdenum specimen is being machined. The chip is quite different in this case. Large blocks of material are fractured from the surface as the tool moves through it. It is very apparent that the surface finish obtained after machining this material is very poor. It can be seen that the molybdenum fails by cracks, propagating through the grain boundaries. The cracks occur at 2 or 3 grain distances below the tip of the tool. They do not form in front of the tool, but rather beneath the tool as it goes through the work surface. A considerable amount of plastic deformation occurs in the chip while it is being formed. This is evident by the metal flow in the workpiece just before it is formed into the chip. Cracks propagate through the grain boundary, even though the material has a modest amount of ductility. Tensile tests of this material have shown that it has a 30% reduction of area. In the following sequence, trace the path that the cracks take during cutting. Sometimes, in going around a grain, the crack will separate into 2 or more branches. The leading edge of a crack can be seen directly beneath the tool point and at a distance of several grain diameters. The crack moves along beneath the tool, seldom going ahead of it. The reason for this type of brittle behavior is the presence of precipitated molybdenum carbides in the grain boundaries. To study the chip formation of a brittle material, a cold work brass is machined. The specimen was previously cold rolled to a 50% reduction of area. As a result, it has very little ductility remaining, and it can withstand only a small amount of additional plastic deformation before it separates into a chip. The chips form with a very steep shear angle and come off the workpiece in small segments. To observe the chip formation of a higher carbon steel, a specimen of annealed 1060 steel is machined. The microstructure can be seen beneath the tool and outside the plastically deformed zone. The microstructure consists of fairly large grains of pearlite surrounded by a network of ferrite. The pearlite grains appear gray and the ferrite is light. The ratio of the amount of pearlite to the amount of ferrite is opposite to the ratio of these 2 structures in a 1020 steel. The chip formation is quite similar to that of the 1020 steel previously observed. The built-up edge is very large and the horizontal cracks are very long. The extent of plastic deformation beneath and in front of the tool can be seen by observing the location of the dark band. Plastic deformation that occurs below the recrystallization temperature of the material results in its being strengthened or work hardened. If the cutting is stopped while a chip is being formed, and the chip and surrounding workpiece are carefully cut out from the bulk of the specimen, it can be metallurgically examined. After polishing the section sample, micro-hardness tests can be conducted around the chip. The results of such a study on a chip of aluminum is shown in the sketch. After a large number of hardness readings are taken in both the chip and the specimen near the tool, a distinct pattern is evident. This pattern is represented by the iso hardness lines, which are drawn to scale. The annealed aluminum has a Knoop hardness of 35. The iso hardness line, labeled 35, indicates the minimum distance beneath the machine surface and also in front of the tool, that the material is not work hardened. The numbers on the lines indicate the location of the material that is strain hardened to Knoop hardnesses of the amount indicated. Although the hardness of the machine surface itself is not shown on the sketch, the hardness at a distance of 1 or 2 thousandths of an inch beneath the surface is approximately 70 Knoop. In the chip, hardnesses as high as 90 Knoop can be found. To obtain an appreciation of how much work hardening is represented by these Knoop values, a similar study was made on a tensile specimen after it was loaded to failure. A longitudinal cross-section of 1/2 of a fractured tensile specimen of annealed aluminum is illustrated. The average Knoop hardness at the threaded end of the specimen, where no plastic deformation occurred, is 35. The Knoop hardness numbers and the corresponding percent cold work that the material had undergone are plotted along the length of the specimen. The hardness increases to 60 Knoop near the neck of the fractured specimen, where the amount of cold work is 64%. The maximum hardness obtained at the neck of the specimen is 65 Knoop, where the percent reduction of area is 87. By comparing the values of Knoop hardness in the tensile specimen to those of the machine surface and chip during low-speed machining, it is evident that there is a thin layer on a machine surface that is work hardened the maximum amount that the material can endure. However, it must be realized that most production machining is done at fairly high cutting speeds, so that the chip becomes hot. At very high speeds, the temperature of the chip will exceed its recrystallization temperature, and the chip will actually soften. Another noteworthy difference between low-speed and high-speed machining is that the built-up edge, which is so prominent at low cutting speeds, does not exist at very high speeds. Consequently, it can be assumed that the chip formation at high speeds is different from that previously observed through the microscope while cutting at low speed. When cutting at high speed, it is very difficult to obtain the proper lighting to clearly show microstructural changes. However, metal cutting researchers have known for a long time that the built-up edge can be eliminated when machining at low speeds if carbon tetrachloride is applied during the cutting operation. To obtain some insight into the mechanism of chip formation when no built-up edge is present, cutting was observed when carbon tetrachloride was used as a cutting fluid. In the sequence to follow, 1020 steel will first be cut dry and then machined with carbon tetrachloride as a cutting fluid. The formation of slip lines in the ferrite grains will be very clearly seen when the tool first starts to cut. Be sure to observe the formation of slip lines in the material directly in front of the tool. Notice that the slip lines appeared before the dark band. There are two distinguishing features between cutting dry and with carbon tetrachloride. One is the incremental shear plane angle, the other the plastic deformation zone. When cutting dry and with a low speed, the plastic deformation zone extends a great distance in front of the tool. The incremental shear plane angle is approximately 25 degrees and varies inversely with the rake angle of the tool. When cutting with carbon tetrachloride, the formation of the chip is seen through a thin liquid film, giving it a shimmering appearance. The chip flows more easily up the tool face, probably due to the presence of a surface film of iron chloride, which has a low coefficient of friction. The plastic deformation zone does not extend as far in front of the tool as when cutting dry. The incremental shear plane makes a larger angle with the direction of cutting, about 45 degrees in this case. A knowledge of the chip formation process is necessary to predict the properties of a part which has been machined, as well as how the part will perform in use later. The surface finish obtained is dependent upon the microstructures in the material, and the surface hardness is equivalent to that hardness obtained by cold working the part to its maximum. Both the finish and the hardness of a machined surface influence the in-service performance of a structural part.